stuff and do the Fourier transforms over those and et cetera. So again, wave packets, any localized disturbance resulting from the sum over many different waveforms, and a Gaussian wave packet is just a particular type of wave packet. So how familiar are you guys with Gaussian integrals?
The only ones that we've done is the Gauss's law in EM.
Oh, that's something completely.
I don't think that's okay.
That's something completely.
So in that case, no law.
Okay, good. So let's first talk about what a Gaussian is. So a Gaussian integral is usually of the form, we're going to call this I of A, which is equal to the integral from minus infinity to infinity of then a Gaussian distribution, which is e to the minus ax squared dx. So this is what's called a Gaussian integral. Okay. So basically, what this is basically a Gaussian distribution. So have you ever seen a Gaussian distribution before?
I think so. I think we did a little bit with that in modern.
Yes.
I'm not sure.
Correct. That's right. So basically what a Gaussian distribution is this is a distribution which is basically centered at x is equal to 0. So this is our x initial, or x is equal to 0. So this is just your typical bell curve. So your typical bell curve is a Gaussian distribution. So basically this has a maximum value depending on how you normalize this thing, but typically we're going to normalize it to 1, at least within quantum mechanics. So x is equal to 0, this is simply 1, and then this falls off as an exponential, basically like this on both sides. Right? So basically it does something like this. What A does here is A controls basically two things. It controls the width here. So this is basically the width. So we're going to call this delta x. We're going to see how this actually controls the width of it in just a minute. So what is delta x? This thing is actually proportional to A in some way. So I'm going to write this as A to the nth power. So basically that controls the width, and the height of this thing is also basically controlled by A as well. So the height here is also proportional to A. So we're not going to look too much at the height, but we'll talk about it. So again, actually, I shouldn't say this is 1 because this is going to depend on A. So the height is actually going to depend on A in some way as well. Okay. I'm going to write this to the nth power. This is going to be some sort of different thing. So this is a Gaussian distribution, and then a Gaussian integral then is basically an integral over then the probability. So this is a probability distribution. So we're integrating then over the probability. And again, we're going to normalize this thing to 1 so that at the end of the day, this is going to have some sort of integration, right? This is going to equal something. So in this case, it's not going to necessarily equal 1 until we put in a normalization. So here, this is just a regular old thing here. So good. Have you guys seen how to actually solve this guy, or what the answer to this guy is?
Somewhere, but I don't have it off the top of my head.
Okay, so I'll leave it up to you. You want to see how to actually come up with the answer, or just what the answer is? That means you want to know just what the answer is. Okay, so that's right. So it turns out that the answer to this Gaussian integral is equal to the square root of pi divided by A. So this is the value of this particular integral. I'll kind of tell you in short, I'll give you a sketch of the way that this actually works. Basically, to do this, you consider I squared of A. And then basically you multiply this by a term that looks just like it, but with a y squared instead. So you're actually going to do a double integral. So here you would do integral dy, integral dx of then e to the minus a x squared plus y squared. And then from here, you're going to turn this into a polar integral instead of a dx dy. So basically, you're going to change this into an integral of the angle of d theta dr. Let me hide my stylus down here. And this is going to become e to the minus a r squared times then the Jacobian. Right? So you guys remember Jacobians from, what is that, Calc 3? So J here is then the Jacobian. So the Jacobian is basically just the equal to the determinant of a matrix, which basically tells you how to transform from one coordinate system to another coordinate system. So here we're going from the XY, so Cartesian coordinates, then into basically plane polar coordinates. So here, let's try to remember which way does this work. So this first row is going to be the derivative of x with respect to r, and the partial derivative of x with respect to theta. So that's the first row. And then the second row is going to be the partial of y with respect to r, and then the partial of y with respect to theta, using that x is equal to r cosine of theta and y is equal to r sine of theta. So basically, if you do that, the Jacobian here, the determinant, you find that's just equal to r. So then you do this integral, again, from 0 to infinity instead, for the r portion anyways. And for the theta portion, it's just going to be from 0 to 2 pi. So anyways, and then when you do that, you find the value of this integral is simply just a over pi, or pi over a, and then you take a square root of that to get the square root of pi over a. So that's basically just a gist of how to go from here to here. So that's where that guy comes from. So that'll be important, not the derivation of it, but basically just this value here, because we're going to use this a lot. Okay. So good. So basically, like I said, so now we have this wave packet. So the first thing we want to see is, so first of all, we want to normalize this because our wave function is going to be equal to that of a Gaussian. Okay. So basically what we want is a Gaussian wave packet in position or momentum space, okay, depending on which one that we want to work with, which means in this case, our wave function is simply going to be equal to this guy. So for a Gaussian wave packet, that means our wave function, psi of x, then is going to be equal to the inner product between x and psi, which is going to be some normalization constant, e to the minus ax squared. Of course, we're not going to use ax squared. What we're going to use is, let's do it this way, minus x squared divided by 2a squared. Okay. So we're actually going to move the a to the bottom. So this is going to be our Gaussian wave packet. Gaussian wave packet. So this is our localized state in the position space. Okay. So good. So first things first, we need to determine exactly what is the normalization constant. So to do that, we're just going to say that 1 is equal to the integral from minus infinity to infinity. Then psi star psi dx, right, which is then going to be equal to the modulus squared of the normalization constant minus integral from here to here, which basically means that this is going to be e to the minus x squared divided by a squared. Dx, right? So this thing here is simply our Gaussian, right? So again, if we go back to our Gaussian here, we have, would you stop doing that? We have I of a, which means in our case, a is actually 1 over a squared. So this is actually just going to be the same thing as n squared integral of 1 over a squared. Right? So that's this value here. Good. So anyways, plug this in and then we can solve for the normalization constant. So basically what this means is following our Gaussian integral, which was the square root of pi divided by a. So if I put that in, then this is going to be the modulus squared of n times then the square root of pi a squared, right? Because this is 1 over a squared, so the a moves to the top, right? Which is the same thing then as the modulus of the normalization constant squared times then the square root of pi times a. So good. So since this is equal to 1, we're going to divide by this term and then take a square root, which means the normalization constant then is equal to 1 over the square root of pi times a. So this is our normalization then of our Gaussian wave packets. So our Gaussian wave packet then is simply equal to 1 over the square root of pi times a e to the minus x squared divided by 2a squared. So this is our Gaussian wave packets. So good. So certain things to know about this is, so basically if I plotted my Gaussian wave packets versus position and I played with A, so let me show you what that actually is going to look like. It looks like this. So this is our typical bell curve. So the blue one is for A is equal to 1. The red one is for A is equal to 1/2. And then the green one here is for A is equal to 1/10. And basically what you can see from doing this plotting, and we'll show how this actually works, is that the smaller we make A, the narrower that this thing becomes, and also the taller that it becomes. Which means that if we took A goes to 0, what'll happen in this case then is it's actually going to have 0 width with infinite height. Other things that we know which have 0 width with infinite height is actually the Dirac delta function. So it turns out that one of the definitions of the Dirac delta function is actually a Gaussian in the limit that A goes to 0. So this is one observation we can make about this. So actually one of the definitions of the Dirac delta function, so Dirac delta, is that if we take the limit as A goes to 0 of our Gaussian wave packets, which is then equal to the limit as A goes to 0 of 1 over the square root of pi times A, e to the minus x squared divided by 2a squared. This thing is actually equal to the Dirac delta function centered at 0. Oh, sorry. Actually, that's not quite true. This is the modulus squared of this guy. So get rid of that square root. Sorry about that. So that was actually the square of it, not the whole thing. So pi a, so I got to get rid of that 2 there. There we go. Okay, would you stop? There we go. So this is actually just over a squared. There we go. So this is true, actually. Good. So good. So what I said in the beginning was that what delta x here basically has to do with the width of this guy. And we said is that this is somehow proportional to A. And by our plotting says that this thing should be somehow proportional to 1 over A, or actually no, directly proportional to A to some power, because again, if A goes to 0, the width of this thing is basically going to 0. Right? So basically what we want to know then is how is the width of this thing then controlled by A? So to do that, to find delta x, we then want to know what is the uncertainty in delta x. So let's look at the uncertainty in delta x. So remember the uncertainty in delta x is then equal to what? To the square root of the expectation value of the position squared minus the square of the expectation value of the position. Right? So this is our delta x. So basically what we want to do then is determine what is the expectation value of the position or the average position in this Gaussian, and then also figure out what is the average squared. So this is then equal to what? X. So sorry, this is going to be psi. There we go. Let's write it this way. So this is going to be psi x psi. Right? So we want to look at this guy. Let's then do a integral over position. So basically first I want to act this guy then onto, so let's do it this way. So let's do A, so I'm going to put an X in here. Okay, so I'm going to put in an identity in this location here. So I'm going to write this as the integral from minus infinity to infinity of then dx psi x hat x psi, right? So now acting this guy into here, as we said before, acting the position operator onto the position basis basically just pulls out the average position that this guy is. So this is going to be equal to then the integral from minus infinity to infinity, then dx times x times the inner product between psi with x and the inner product with x with psi. But again, we know the inner product with x with psi is simply equal to our wave function. So then the average position then is equal to the integral from minus infinity to infinity, dx x times then psi star psi. Now in this case, since we're looking at the average position for the Gaussian wave packets, Again, our psi is simply going to be equal to 1 over the square root of pi times a, e to the minus x squared divided by 2a squared. So we want to modulize this with the wave packets. So this is going to be equal to minus infinity to infinity dx times x times e to the minus x squared divided by a squared, and I get a factor of 1 over the square root of pi a out front. So this is then the expectation value of the position, or the average possible position for this guy. So from here, I have 2 methods I could do with this. I can actually do this integral, which I don't feel like doing. The other way I can think about it is what? So again, let's plot our Gaussian here. So again, this guy is simply this, which means that this guy is an even function. If I plot x on top of that, x is actually an odd function, which actually does this guy. So this is an odd function, which means the product of then x with our Gaussian is actually what? Also an odd function. And what we know is that what this guy looks like would be the superposition of these 2 things, which means that this value here, right, our integrand, let's call that our integrand. So that's going to do, it reflects this one down to this side. So this guy is actually going to do what? Ride along this and then do something like that. This side over here is going to reflect on this side. So this is going to look something like this, right? Which means I have as much on this side as I have on this side, because overall this is some odd function, which means if I integrate from minus infinity to infinity over an odd function, what do I get?
0.
0, good. So automatically I know that guy's simply equal to 0. Good. Done. Life is good. All right, so that's easy. So now we want to do the same thing with the expectation value of the position squared. So following this guy and what we actually did here, differences is going to be x squared. But when I act x squared onto it, I get 1 factor of x when I act on it the first time, and then I get a second factor of x, which means the only difference is this is going to become an x squared instead of an x. Which means that here, this is still going to be equal to 1 over the square root of pi a, integral from minus infinity to infinity, then what? Dx times x squared times e to the minus x squared divided by a squared. So, cool. Now here, again, this is an even function. This is also an even function. So what happens if I take an even function times an even function? What do I get?
Another even function.
You get another even function, which means that this thing is no longer equal to 0. So any other way I can kind of see that is, again, if I plot my Gaussian, so my Gaussian is doing this, right? X squared does this, oops, a little bit of curl in there, but that's okay. Which means that if I, again, superimpose these guys on top of each other, my overall function is gonna, what, ride this guy and then come up and go down like this, come up and then follow this guy on this side. So my overall function is even, which means I have as much on one side as I have on the other side. Which means that the average position is not going to be 0 anymore, but it's going to be somewhere more in this kind of section here where I have a higher probability, right? So unfortunately, this thing is an even function, which means that we actually have to do an integral. So let's look at that guy. So the first thing I'm going to do is I'm going to define some new b, which is equal to 1 over a squared. Okay, so I'm going to basically move that b to the, move that 1 over a squared to the top, just to make my life a little bit easier. So good. So this integral then is going to be equal to, again, 1 over the square root of pi times a, integral from minus infinity to infinity, dx of then x squared times e to the minus bx squared. Okay. Now, one thing I want you to note, and this is a trick I'm going to kind of teach you guys, because learning new math tricks is always fun. Notice that if I had just the exponential here, if I took the derivative of the exponential with respect to b, that would actually pull down then a negative x squared, right? So notice that if I took a ddb of e to the minus bx squared, this is actually equal to what? minus x squared e to the minus bx squared, right? Does that make sense?
Yeah.
Good. So basically what I'm going to do is I'm actually going to replace this factor here with actually this with a negative sign, right? Which means I'm actually going to rewrite this as negative of 1 over the square root of pi times a integral from minus infinity to infinity integrated over x of then d db of e to the minus bx squared. Right? You guys doing okay? Does that mean yes?
Yeah.
Okay.
Sorry.
So notice the integral is over dx, but the derivative is over b, which means I can actually pull the derivative outside. Right? Which means I can actually rewrite this then as minus 1 over the square root of pi times a, the derivative with respect to b of then the integral from minus infinity to infinity dx e to the minus bx squared. Right? So basically what this says is that the value of this integral here is the same thing as the derivative with respect to b of the value of this integral. Right? Doing okay? But this integral here is simply our Gaussian integral, which depends on b. So this is the same thing then as 1 over the square root of pi with my negative sign. Can't forget my negative sign. A times the derivative with respect to b of the value of the Gaussian integral, which depends on b. That's doing okay? But we already know the value of that Gaussian integral, based off what we did way back here, is equal to the square root of pi divided by b, because here a is just the same thing as b. So let's plug that in. So finally, this becomes negative 1 over square root of pi times a times the derivative with respect to b of the square root of pi divided by b. Now, let me kind of explain the utility of this and why this is actually more useful and what we're ignoring. So what we're basically ignoring here is to do this integral, I'd have to do integration by parts. Right? So basically here, I would have to define this as my, what? The e to the minus bx squared dx as my dv. And then u would be then my x squared, which means we'd have to do integration by parts twice onto this to get to basically the same answer. So this is actually a lot easier way of doing this particular integral as opposed to actually having to do integration by parts.
Gotcha.
The more you know. So good. So this here is the same as this because that's a constant, so I can actually get rid of that guy, right? So this says then that the expectation value of the position square then is minus 1 over a times then the derivative with respect to b of then b to the negative 1/2. So good. So now let's plug that in. So if I take a derivative of b to the negative 1/2 with respect to b, so first thing I'm going to do is I'm going to get that negative 1/2 down. So that's going to cancel that negative, make it a positive. So I'm going to get a 1/2. 1 over a stays, and then I get the derivative of that, which then becomes what? B to the minus 3/2, right? That's doing okay. But again, b is actually equal to 1 over a squared, right? Which is then equal to what? A to the minus 2. So let's plug that in. So this guy becomes 1 over 2a times then a to the 3rd. So this becomes simply a squared over 2. As I say, I cancels with one of those. Guys doing okay?
Yeah.
So finally, the uncertainty then is going to be equal to the square root of the expectation value of the position squared minus the expectation value of the position squared. Well, again, we know this term is simply equal to 0. This term is non-zero, so this becomes equal to the square root of a squared divided by 2, which is then a divided by the square root of 2. Okay. So basically what this says then is that the width of our Gaussian here, our Gaussian distribution or our Gaussian wave packet, delta x, is then simply equal to a divided by the square root of 2. Which means then that what? As a gets smaller, delta x also gets smaller by exactly the same amount. Okay, so it's linearly proportional to a. You guys doing okay?
Yeah.
So now, so that is then how a controls the width. I'm not going to bother worrying about the heights because it's a, well, I won't even bother with it. So that's fine. Now, the other thing we said before, or at least last time, was that what? When we do a Fourier transform, what happens is if I took a well-defined state in position, so if this is my position and this thing was well localized about some, say, x is equal to a, when we did our Fourier transform, or we transferred that thing from position space into momentum space, what happens then is that this thing becomes delocalized in position space, so, or sorry, momentum space, so this thing ends up doing something like this. Right? So if this was momentum, which means that what? If this thing had a delta x width to it, as delta x gets smaller, which should happen to this thing then is that the spread of this guy actually becomes bigger. Right? So as this guy goes down, this guy is going to go up. So basically what that means is we want to see that happen then for our Gaussian wave packets. So we want to first do a Fourier transform of our Gaussian wave packets from position space then into momentum space, see what actually happens to that guy, and then see how the width of that changes with A. Probably shouldn't have called that A in hindsight because I'm already using an A. Let's call that X0. There we go. Good. Guys doing okay?
Yeah. Oh.
Let's find then our momentum representation of our Gaussian wave packet. So in this case, we want to know what is psi of p, which we know is equal to the inner product with p with psi. Okay. Now, as we talked about, to turn this from position space into momentum space, last time what we saw is all we're going to do is insert an identity in here, which is then a superposition over the position states. So I'm going to write this then as the integral from minus infinity to infinity over dx of then p x psi. So this is my Gaussian wave packet again. And then this was my transformation matrix from position space to momentum space. And remember last time we found that the transformation matrix from momentum space to position space was equal to, make sure I get my constant right here. So this is equal to 1 over the square root of 2 pi times h bar e to the, so this was in the positive, so this was I times p times x divided by h bar. Okay. So here, this is just a complex conjugate of that, so everything stays the same except for this becomes a negative sign. So let's put all this stuff together. So this is then going to be equal to integral minus infinity to infinity dx times this guy. So it's going to be 1 over the square root of 2 pi h bar e to the minus I px divided by h bar times then my Gaussian wave packet, which is 1 over the square root of pi a e to the minus x squared divided by 2a squared. Huh? That's doing okay?
Quick question.
Sure.
Is the h bar on the inside of the square root or the outside?
Inside. There. Good. So let's put all the prefactor together. So this becomes 1 over the square root of 2 times pi to the 3/2 times a times h bar. So that's all my prefactor. Ugly prefactor, but it's a prefactor. Integral minus infinity to infinity of then, so now I get a dx e to the minus x squared divided by 2a squared minus I px divided by h bar. That's doing okay? So basically, to do this integral, we're going to do something called completing the square. So notice that here I have a square term. This looks like a cross term, right? Because I have a momentum term times a position term, which means I can complete the square by adding on here something that looks like momentum squared, right? So that way I'm basically going to rewrite this as the exponent here. I want to rewrite this as something that goes as x plus some other factor times p quantity squared. So basically I have a factor maybe on x, I have a factor on the p, but I basically want to rewrite this by adding something here, which is going to make it so that I can complete the square, and then I have a leftover term. So turns out the way to do that is, so in this case, the prefactor becomes, let me write out psi of p then, is equal to, let me get my prefactor again, so the square root of, so this was what, 2 pi to the 3/2 ah bar, integral minus infinity to infinity, dx of e to the, so now I'm going to get a minus 1 over 2a squared times x plus IPA divided by h bar quantity squared minus p squared a squared over h bar squared. So basically what I'm doing is 2h bar squared. So basically I'm adding in this term, I'm adding a plus and minus of this term, and then combining that with here to then factor out to make sure that I can write a squared term. So this is what's called completing the square. Now, notice here that this is one exponential term of this guy times the second exponential term of this guy, but this guy here doesn't depend on position, it only depends on momentum, so I can actually factor that guy out from the integral. So this becomes equal to the square root of 2 pi to the 3/2 ah bar 1 e to the minus p squared a squared divided by 2h bar squared, integral minus infinity to infinity, then dx e to the minus 1 over 2a squared, x plus IPA divided by h bar quantity squared. Now from here, what we're going to do is define a new x prime, where x prime then is equal to the original x plus IPA divided by h bar. Now, the reason we're doing that is basically what I want to do is turn all of this here into some x prime. I don't want to worry about this extra term, because notice that if I take a derivative of both sides, I end up with dx prime and is simply equal to dx. So by rewriting this guy, what that means then is that this is going to become equal to 2 pi 3/2 ah bar square rooted e to the minus p squared a squared divided by 2h bar squared, integral from minus infinity to infinity, dx prime e to the minus x prime squared divided by 2a squared. So by making this substitution, basically a u substitution here, I've now turned this ugly looking integral into simply another Gaussian integral, where this is now a Gaussian integral, which depends on 1 over a squared. Actually 1 over 2a squared. Okay. Where again, the value of this integral is simply equal to 1 over or the square root of pi divided by a squared. So this becomes 2a squared on top. So what's the value of this integral? So again, the reason that I'm doing this, defining this new x variable, or again, doing basically u substitution, is that I can turn, again, this ugly looking thing into simply a Gaussian integral where I know the value of this Gaussian integral. Life is good. So good. So all this stuff here just basically goes into the prefactor. So this finally becomes, so let's write all this out, the square root of 2 pi a squared divided by 2 pi to the 3 halves a h bar times then this exponential here, which is then e to the minus p squared a squared divided by 2 h bar squared. So finally, this 2 cancels this one. This pi is going to cancel this to make that a square root. This a cancels this a. So finally, after all is said and done, we get the momentum space Gaussian then is equal to the square root of a divided by the square root of pi times h bar e to the minus p squared a squared divided by 2 h bar squared. Whew. That was a lot. So the overall gist of this is that what? If we had a Gaussian in position space, doing a Fourier transform of that to momentum space also gives us a Gaussian. This thing is still just a Gaussian. So this then gives us a Gaussian in momentum space. So the interesting thing about Gaussians is a Fourier transform of a Gaussian is still a Gaussian. And that's true going back in the opposite direction as well. If we did the inverse Fourier transform going from momentum space to then position space, we would still then have also a Gaussian. So the Fourier transform of a Gaussian or the inverse Fourier transform of the Gaussian is still a Gaussian. But notice what happened is the a squared went from the bottom to the top, which means that a then is going to control the width of that guy slightly differently now, right? Because before, as a went to 0, then the width of it went to 0. But here, since this guy is on the top now, actually the opposite effect is going to happen. As a goes to 0, this thing is actually going to become wider, which means that it becomes more localized again in position, then it's going to become less localized then in momentum. Does this make sense?
Yeah, I think so. Sort of.
So let's see that. So again, what happens is we took this guy and again, position. So here is our Gaussian, again, centered at 0, where this guy had a width of delta x, where we found delta x was a over the square root of 2. Which again meant as a goes to 0, the width of this thing goes to 0. So now what we have is a Fourier transform into momentum space. So again, this thing is simply a Gaussian. So here's my Gaussian. This thing is centered at 0 momentum again, just like the position is 0 to add 0 position. But this thing is going to have an uncertainty, delta p. And if this thing becomes more localized as a goes to 0, then what should happen then is that this one should become less localized, which means in the limit that a goes to 0, what should happen then is that delta p should go off basically to infinity. So I should have a opposite effect as this guy. So let's show that's true. So now what we want to do is figure out what is the uncertainty in the momentum. So again, it's going to be equal to the square root of the expectation value of the momentum squared minus the expectation value of the momentum quantity squared. So this is the square of the momentum minus that of the momentum quantity squared. So good. Let's look at this guy first. I'll do the full argument that we did before. So this is then equal to psi p psi. Right. Technically, this is p of x. So let's write it as p of x to be all good. So again, all I'm going to do is I'm going to insert an identity here, where I'm going to use now momentum space instead of position space. So this is going to become equal to the integral minus infinity to infinity of then dp of then psi px hat p psi. Again, we know this guy acting onto him is simply going to give me a p, so the momentum. So I'm going to have the integral from minus infinity to infinity dpp, and then I get the inner product between psi p psi. But again, this is just the momentum, or the Gaussian wave packet in momentum space. So I have two factors of that. So this thing is going to become, so let's do it this way. So this is going to be equal to minus infinity to infinity of dp. Actually, I'm going to write just proportional. I don't feel like writing all that prefactor out. So I'm going to be lazy here for a second. There we go. E to the minus p squared a squared divided by h bar squared times p. Again, this guy is an even function. This guy is an odd function. So if we integrate over an even function and an odd function, that becomes an odd function. What happens if we integrate over an odd function over all space?
0 again.
0 again. Good. So that guy is simply equal to 0. What's that?
What?
I thought somebody said something. So. We like integrals that are 0. Life is good. Okay. So good. So that's that guy. So again, we're going to do the same thing with p squared. So p squared then is going to be equal to the integral minus infinity to infinity dp. Now I just replace this with the momentum squared. And then again, I get a modulus squared of psi. So good. Let's put all that in. So this is now going to become, using our prefactor. So this is a over the square root of pi times h bar, integral minus infinity to infinity, dp times p squared of e to the minus p squared a squared divided by h bar squared. Again, if we do the same idea that we did before, we can simply write b then is equal to a squared, so that this becomes minus b times, actually, I'm going to roll in the h bar squared. So I was going to put this as b is actually a divided by h bar quantity squared. All right. Do the same trick as before. Write this as then a derivative with respect to b. Go through all of that. I'll let you guys fill in those steps for yourselves. But basically, if we go through all this, what we find then is that this becomes h bar squared divided by 2a squared. All right. Which means then the uncertainty in the momentum then is going to be equal to the square root of this guy. So h bar squared divided by 2a squared, which is then equal to what? H bar divided by the square root of 2 times a. So again, going back to what we wrote down before, what we expected should happen is, again, as a goes to 0, delta p should go to infinity, which it does because it goes as 1 over a. So delta p then is equal to h bar divided by the square root of 2 times a. So again, the width here is also controlled by a, but it's controlled inversely by what delta x is. So again, if I have a well-localized state in position, a Gaussian wave packet, Fourier transform that, I still get a Gaussian wave packet. But again, the difference is the smaller a becomes, the more delta-like function this one becomes, which means this one has to become infinitely spread out. So delta p, again, is going to go to infinity. Now notice, the other thing is, what if I take the uncertainty in the momentum times the uncertainty in the position, then this is equal to a divided by the square root of 2 times h bar divided by the square root of 2 times a, which means the a's are going to cancel, because again, one is inverse of the other one, which means this is h bar divided by 2, which means that this thing satisfies the Heisenberg uncertainty principle. Not only does it satisfy, but this is the minimum uncertainty that we can have, because remember, Heisenberg uncertainty principle says that this has to be greater than or equal to h bar divided by 2. So if it's exactly equal to h bar over 2, this is what's known as a minimum uncertainty state. So a Gaussian wave packet is actually what's called a minimum uncertainty state, in the fact that it satisfies the Heisenberg uncertainty principle, but it satisfies it at the smallest possible way. So when it's exactly equal to h bar divided by 2. Just show you some plots here. So again, here, as we said, as A gets smaller, this thing becomes sharper in the probability for the Gaussian wave packets. If I do the same thing with the probability for the Gaussian wave packet momentum space, we see the opposite effect. So here, this is when A is equal to 1. Red then is when A is equal to 7/10. And then green here is when it's equal to 3/10. So again, the smaller that guy gets, the more spread out it actually becomes. Sorry. Short out front. Okay, they're going away. I don't have to close the window. My new shoes are here. Yay. Okay. So, guys doing okay?
I think so.
Good. So, good. So the next thing we want to know is, how does the Gaussian wave packet evolve with time? So this is the next thing we're going to start looking at. So we want to look at the time evolution of our localized states, so of our Gaussian. So basically, again, what this means is, if this is our x-axis, we start off with some well-localized state, which is a Gaussian, at some initial position. So let's say, again, same thing as before, this is at x is equal to 0. This is our position. What happens then to this well-localized state as time evolves? So let's say this is at t is equal to 0. But what happens if we evolve this guy with time? So we have u of t0. So we evolve this to some non-zero time. What happens now? Does this thing get smaller? Does it get more spread out? Or does it stay the same? So if this is, again, x0. So does it, say, in the blue, stay the same? It's supposed to be the same. So does it stay this way? Or does it, say, devolve with time? So it does something more like this. So it gets more spread out. So does it devolve? Or does it become more localized? So does this thing actually become something more delta function like? So does it localize? So questions are, if I evolve this thing with time, does it stay the same? Does it become more localized, or does it delocalize or devolve? So delocalize. So does it become more spread out? So the question is, which one of these three does it do? Now, here we're going to look at a very special case. We're going to look at the time evolution of a free particle. So ultimately, the answer to this is going to depend on the potential, but we're going to look at a free particle, which means that the potential is equal to 0. So this thing has no binding potential. Now, if we do have a binding potential, then that's going to change this answer, obviously. But here we want to look at just this one particular case of a free particle. So what happens to this guy? Good. So what this means then is that our Hamiltonian is then equal to the momentum operator squared divided by twice the mass. Because again, the potential is equal to 0. So this is now our Hamiltonian. So good. So basically, we're going to look at our time evolved states. So here's our time evolved states. Now, again, we know our time evolved state is going to be equal to the time evolution operator, acting then onto the time is equal to 0 states, where in this case, we want to take our time is equal to 0 states as our Gaussian wave packets. Okay. Good. Now, in this case, what do we know? So we know that since the moment or the Hamiltonian only depends on the momentum operator, what that means then is that what? The momentum basis which is an eigenstate of the momentum operator, then has to also be an eigenstate of the Hamiltonian, which means that our energy eigenstate here is simply equal to our momentum basis. Okay? So our momentum state is equal to our energy eigenstates in this case. In a more general case, that's not always going to be true, but typically, at least here, this is going to be true. So basically what I'm going to do then is I'm going to, again, insert the identity here, but I'm going to insert it so that I'm going to do an expansion of this in terms of the momentum eigenstates. So this is going to be equal to the integral from minus infinity to infinity of then dp of my what? Yeah, so let's do it this way. So I'm going to put in my time evolution operator here. And then we're going to get a p psi. Right? Now, in this case, since this Hamiltonian is actually independent of time, what we know then is that our time evolution operator, I'll write it over here, is simply going to be equal to e to the minus I Hamiltonian times the time divided by h bar. So that's going to be this guy. So let's use the guy into here. So this is going to be equal to the integral from minus infinity to infinity dp of then e to the minus I Hamiltonian t divided by h bar p psi. Okay. Sorry, and this is time 0 psi. You guys doing okay? Now from here, h we know is simply equal to p squared divided by twice the mass, which means that what? This is going to be e to the minus p squared times time divided by twice the mass. But then I would do a Taylor series expansion of that, act each one of those p's onto the momentum basis, which means that the momentum operator simply is going to become the momentum. So let's write that down. So finally, what I get is my time evolved state is then equal to my integral from minus infinity to infinity of my momentum. And then this is going to be e to the minus momentum squared times the time divided by twice the mass times my momentum basis times the inner product between the momentum basis and psi at time is equal to 0. Now, since we want to know what happens in position space, how does this guy actually evolve in position space? I'm going to take all of this now and then project it into position space by acting on it with a raw version of my momentum. Sorry, of my position. So finally, I'm going to get a x psi of t, which is simply equal to the wave function at some position at some time t, which is then going to be equal to the integral from minus infinity to infinity dp. Now, since this is now just a number, I'm actually going to pass this raw version of x right past him. So this is going to be an e to the minus p squared t divided by 2m. Now I'm going to get the inner product between x and p, and then the inner product between p and psi at t is equal to 0. Now, again, this guy is just a transformation matrix, which goes from the momentum space into position space. We already know what that guy looks like. This is now just the momentum version of the Gaussian wave packet. We already know what that guy is. So let's go ahead and plug all those things in. So this is going to be equal to, so this guy comes with a, what does he come with? He comes with a 1 over the square root of 2 pi h bar. This guy comes with a square root of h bar divided by the square root of pi times a, right? The a on the bottom. The a on the bottom. Yeah. And then I get a minus integral from minus infinity to infinity, and then dp e to the minus p squared t divided by 2m. And then this guy is going to give me a, what? So e to the I, px divided by h bar. And then this guy gives me an e to the minus p squared times a squared divided by 2h bar squared. Guys doing okay? Oops, I forgot my I on these things. Should be an I there. I. Okay, good. Sorry. Remember, there's a negative I in front of the Hamiltonian, so I got to put that I in. So it should be an I there. Good. So now let's put terms together. So this term here comes with a p squared. This one comes with a p squared as well. So let's go ahead and put those guys together. So let's do all that. So what should happen here then is, so this prefactor, I think I wrote down the wrong prefactors, but whatever. So this becomes a divided by 2 pi to the 3/2 h bar squared. At least that's what it says in my notes. So we're going to go with that. And then I have the integral from minus infinity to infinity of dp. And then I'm going to get an e to the minus p squared divided by 2h bar times. Now from this one, I get a I times t divided by m, right? Because I also forgot my h bars here. And I'm forgetting a lot of terms. And then from this one, I'm going to get a plus a squared. And that's it, right? No, divided by h bar, because I have an h bar squared. I pulled out an h bar. Good. And then I get this term, which then gives me a plus ipx divided by h bar. You guys doing okay? Good. So this guy goes as something as p squared. This one goes linear in p. So I'm going to define this then as the square root of a divided by 2 pi 3/2 h bar squared integral from minus infinity to infinity of dp times e to the minus, let's call this cp squared plus b times p, where c is then equal to what? All this stuff here. So this is going to be equal to 1 over 2h bar times it over m plus a squared divided by h bar. And then b is going to be equal to what? I times x divided by h bar. So this is my b. Guys doing okay? Now this one here, we can do some basically magic as we did before. So from here, what we can do is, again, we can do completing the square. So basically, we have a term over here that goes proportional to b squared, which means when we add that term onto here and subtract that term, then this thing is going to become what? A complete square. So basically do the same thing that we did before. And then once we have this as a complete square, we just redefine the momentum as some momentum prime. So we do the same thing. So basically this thing becomes simply a Gaussian integral, which we already know the answer to, times an exponential, which depends simply on p squared, or sorry, b squared. So I'm not going to go through all that, but I'll show you what it actually looks like. So basically what we find is that psi of x of t ends up becoming the square root of a divided by 2 pi to the 3/2 h bar squared. Then I get an e to the b squared divided by 4 times c. So that's the extra term that I had to add on to there, times the net Gaussian integral, which is then the square root of pi over c. So anyways, good. So once I finally put in what a and b are and all that kind of good stuff, what I finally get then is this works out to be equal to 1 over the square root of pi times a plus ih bar t divided by ma 1 over e to the minus x squared divided by 2a squared times 1 plus ih bar t divided by ma squared. So that's the value of all this beautiful stuff. Okay.
Is that x squared over 2h bar squared?
Oh, that's a 2a.
Oh, okay.
That's an a squared, and then there's an h bar inside of that stuff.
Okay.
Now, if we do exactly the same thing and compare to what we had before, so basically what's happening now is I'm just getting this extra term attached to A, which means if we go back to what we did earlier, what we'd find then is that the uncertainty then into position basically goes as A divided by the square root of 2 times the square root of 1 plus h bar squared t squared divided by m squared a to the 4th. So let's talk about this. So basically what this says then is that what? As time goes off to infinity, what happens then is that the uncertainty or the width of this Gaussian actually is going to delocalize. So if initially this thing has some width to it, delta x, which is equal to a divided by the square root of 2 at t is equal to 0, what this thing says then is that as time goes off to infinity, what happens then is that what this term becomes bigger and bigger and bigger and bigger, which causes this thing to actually delocalize and actually become more spread out. So as time actually increases, this thing is going to do something like this, right? Until eventually, as time goes to infinity, this thing has infinite uncertainty to it. So as time goes to infinity, this thing is basically going to be a nice flat horizontal line. So as t goes off to infinity, of course, the height of this won't be as high. It's actually going to go somewhere down here, actually. So I should move this guy down to here. So it's actually going to do this. So that means that, again, if this thing is well localized at time is equal to 0, this thing actually is going to spread out and become completely unlocalized as time goes off to infinity, right? Now, the reason for this is the fact that the potential is equal to 0. So since there is no binding potential, this thing then has the probability of spreading out everywhere and basically become what? Located anywhere in space. So if this thing has a probability of being located anywhere in space, that makes sense then that the uncertainty then has to go to infinity, because basically you can find it anywhere, right? So again, as t goes to infinity, then the uncertainty then for this guy has to go to infinity. Does that make sense?
I think so.
Good. So the question then is, okay, well, what happens to the momentum? So basically we want to do the same thing for the momentum. So if it becomes delocalized in position space, well, what then happens in momentum space? So what happens in p space? So does this guy actually become more localized than in p space? So if this thing is, again, in position space, going from a localized state around x is equal to 0 at t is equal to 0 to basically something that kind of does that, right? As time goes off to infinity. So what happens then in momentum space? So if this was in momentum space and this thing is, but if this is our momentum equal to 0, so if this thing was a slightly bigger width to it, right? Because again, these two things are inversely proportional. So if this thing was well localized, this thing isn't quite localized at, say, t is equal to 0. So my question now is, well, if this thing is becoming delocalized, so is this thing actually now becoming localized as t goes to infinity? Is this true? Well, let's find out. So let's do that. So basically, let's now look at the inner product between the momentum and our time evolved states. So let's look at this guy. So this is now going to be equal to, I'm going to have some normalization constant out here, so I'm just going to call that n. Integral from minus infinity to infinity of then dp times e to the minus I p squared t divided by 2mh bar, right? That comes from my Hamiltonian. But now we're going to get then is the inner product between p, actually let me call this p prime, just to make it something different. P prime with then p, and then I get a p with psi, right? Well, what's the inner product between p prime and p?
Dirac delta.
That's a Dirac delta, right? So this is actually the inner Dirac delta between p and p prime, which means this is going to be equal to what? N integral minus infinity to infinity of dp e to the minus I p squared t divided by 2mh bar, Dirac delta p prime minus p of then psi of p. But now when I do the integral over p, that's just going to change all the p's to now p primes. So this is now just going to be equal to n e to the minus I p squared t divided by 2mh bar.
Allahu Akbar, Allahu Akbar.
That again.
Allahu Akbar, Allah.
Sorry, second time that's happened. Good. Times then psi of p prime. So now what? So now notice what's actually happening is if I look at the modulus squared of this guy, so if I look at the modulus squared of p prime psi of t, what happens then is what? So let's go back. I'm going to get an n squared. This term is going to go to 1 because it goes with an I times simply this guy. But this is the wave function at time is equal to 0. So what this means is that this is actually equal to simply p of psi of 0. So basically what happens is what? The probability of measuring it at some later time is exactly the same as the probability of measuring at the initial time, which basically means that what? No, it doesn't delocalize. It actually stays at exactly the same as it was before. The only thing that happens is, according to this guy, is it picks up a random phase basically out front, which evolves it in time, but this phase doesn't actually change anything about the localization of it. So this thing actually does not delocalize at all. It actually stays exactly the same. So momentum space, this thing stays the same, but in position space, it actually delocalizes, which means that basically it goes from a minimum uncertainty state to now not a minimum uncertainty state, but it still abides by the Heisenberg uncertainty principle. Since this one ends up with infinite uncertainty, this one stays with the same amount of uncertainty, which means that it goes from a minimum uncertainty state to something which doesn't have minimum uncertainty anymore. Guys doing okay?
Yeah.
All right. So I think we'll stop there for today. So basically what we'll start off with next time is we'll write down now the Schrodinger equation and then talk about general properties of the Schrodinger equation, talk about the energy eigenstates, look at now some square wells and do all kinds of fun stuff, and then talk about general properties of it, and then talk about scattering. So I think next time we'll start with all that kind of good stuff. All right. All right. So I will see you guys on Tuesday in person. Life will be great.
Okay.
All right.